Uh, okay, so hello everyone. Thank you for coming to my talk. I'm very glad to be here at beautiful Amsterdam to communicate with all the Spark lovers. So today I'm going to give update to Project Hydrogen, unifying the state-of-the-art AI and the big data in Apache Spark. So a few words about myself. I'm Shimbo Jiang from Databricks, and currently I'm focused on Spark core module. I'm also a committer of Apache Spark. First, please let me introduce Project Hydrogen. Announced last June, Project Hydrogen is a major Spark initiative to unify state-of-the-art AI and big data workloads. It contains three major components: data execution mode, which has been delivered with Spark 2.4, optimized data exchange, and accelerator-aware scheduling, which would be delivered with forthcoming Spark 3.0. As a data scientist and data engineer, we are all familiar with Spark, and we all know AI. But why should we connect Spark with AI? What would be the benefit to integrate AI workload better with Spark? So about Spark, Spark was initiated at 2009, so it has been 10 years history. Apache Spark is the first unified analyze engine that covers both big data processing and machine learning. It's high performance, it's easy to use, and it combines SQL, streaming, and complex analytics. It can run everywhere on Hadoop, Mesos, Kubernetes, on standalone mode, or in the cloud. Spark is the most popular data analysis platform now. In the meanwhile, AI is reshaping the world. Huge innovations are affecting most enterprise on the planet. For example, we use AI for healthcare and genomic, for fraud prevention, for digital personalization, for Internet of Things, blah, 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 and many more applications. So with the deep learning technology innovation, the correlation between the amount of data and the performance of the model has been rising. With traditional machine learning models, the performance stops growing fast when the amount of data reaches a limit. But with deep learning models, the performance continues improved as more data are provided. So the trend is the best models are requiring more and more training data. When the training data set gets bigger and bigger, we see more and more distributed training scenario and open source offering. For example, distributed TensorFlow, Horovod and Distributed MXNet are coming out. This is where Spark and AI cross. Now, we realized it creates great value to integrate AI workload with Spark, but why would Project Hydrogen be the right answer? What are the specific problems with better integration, and how Project Hydrogen would resolve these issues? Let's start with two simple usage. As a data scientist, I want to build a pipeline that fetches training events from a production data warehouse and train a deep learning model in parallel. Also, I want to apply a trained deep learning model to a distributed stream of events and enrich it with predicted label and then write them back. For the first use case, I need to load data from a data source. It might be a reliable storage layer that supports transactions like data lake, or it might be some data source format like Bakui, or extended or external database or cluster like MySQL or Hive. We also already know Spark is good at handling such job, since it has built-in support for almost all the major data source formats. On the other side, I shall launch a distributed GPU cluster for faster training, to which the answer might be Horovod, might be distributed TensorFlow or other AI platforms. This sounds good, but maintaining two separated data and the AI cluster can be still painful and error-prone, and it's also less efficient. I need to write glue code to maintain the sequence of jobs running on the separated clusters. Also, I have to spew and then fetch data to remote storage, which brings extra burden. Thus, I would like to have a single cluster that can handle both the data processing workload and the training job. For the second usage, I might read data from a streaming data source and apply the trained model on these events, which might require GPU for faster inference, and then save the results to stream sync again. On a hybrid Spark and AI cluster, the two use cases can both run smoothly. For the first, I can start a job to load data using a Spark cluster with GPUs, followed by another job that feeds a model distributedly on the same cluster, and then output the trained model. For the second, I could load the events using a Spark cluster with GPUs, then load the model and predict with GPU as a Spark task, and at last, write the result back to the streaming data source. But unfortunately, before Project Hydrogen, the hybrid cluster solution doesn't work out of the box. To address the limitations, we started working on Project Hydrogen. Now, all the major features have been implemented and should be shipped with the forthcoming Spark 3.0. So, Project Hydrogen proposed three major components to fill the major gap, namely barrier execution mode, optimized data exchange, and accelerator-aware scheduling. Here, as a Spark contributor, I want to present what features from Project Hydrogen are available and what features still need further improvement. As a Databricks engineer, I want to share how we utilize features from Project Hydrogen and lessons learned as best practice integrating Project Hydrogen with real-world workloads. To fully support the first use case, we need to support the distributed training of machine learning models on Spark. Thus, we introduce barrier execution mode, which fills the gap between the traditional Spark execution mode and that required by distributed training of machine learning models. Let's go deeper into the difference. Barrier execution mode is different execution model from the traditional MapReduce execution model in Spark. In MapReduce execution model, tasks are independent of each other, and also each task runs in parallel and massively scalable. For distributed training, the requirement is not exactly the same. In distributed training, it requires complete coordination among tasks, and also each task should be optimized for communication. We introduce barrier execution mode to Spark on top of MapReduce execution model. So a distributed machine learning job can run as a Spark job. The barrier execution mode starts all tasks together. Also, it provides sufficient information and tooling to run a hybrid distributed job. For failure handling, the barrier execution mode cancels and restarts all tasks in case that at least one task failed. The user interface of barrier execution mode is straightforward. For RDD, we add a new API, RDD.barrier, that tells Spark to launch the task together. When you call RDD.barrier, the corresponding workload will be running under barrier execution mode. For each single task, we added context.barrier that places a global barrier and wait until all tasks in this stage hit the barrier. This provides the exact behavior to let all tasks achieve global synchronization, which is critical for machine learning workloads. To fulfill task coordination requirements, we added context.getTaskInfo that returns information about all tasks that's running in parallel. Through context.getTaskInfo, every task can start connection with other tasks that are running in parallel, so they can perform perfect communications. Let's see how barrier execution mode is integrated within Databricks. So barrier execution mode is integrated within Databricks to run Horovod. Horovod is a distributed training framework for TensorFlow, Keras, PyTorch, and MXNet. It is originally developed at Uber, now a Linux Foundation AI-hosted project. It requires little modification to single-node user code to make it distributed. Also, it provides high-performance I/O through MPI and SCCL. Also, it has same convergence theory with single machine models, while it also has some limitations. For example, before version 0.16, users still need to use MPI ROM to launch a job. And basically, the job needs to start with Python training script. So Databricks have integrated the HorovodRunner with runtime 5.0 built on top of Horovod and the Project Hydrogen. The product runs Horovod under barrier execution mode. It also has detail like cluster setup, the script, the MPI command line from users. The integration of Horovod with barrier execution mode is straightforward. First, we shall pickle and broadcast the train function, which shall inspect the code and warn user about potential issues. Then, we launch a Spark job in barrier execution mode to run these functions. In the first vector allocated, we shall use worker address to launch the Horovod MPI job. And then, we can continue execute the model training. If the Spark job got cancelled, we shall terminate Horovod finally. The limitation is most about dependencies. Since the product is tailored for Databricks runtime ML, and it uses Horovod, it needs to be built with TensorFlow, PyTorch, SSH, OpenMPI, SCCL, and other packages. Also, since it's built on barrier execution mode, it is only available since Spark 2.4. And if you try to utilize accelerators like GPUs, you need to modify the cluster configuration to accommodate that. The next major component is accelerator-aware scheduling. It allows tasks in Spark to utilize accelerators to speed up computation. Accelerators, known as GPUs, FPGAs, and other names are widely used for accelerating specialized workloads like deep learning, like signal processing. To utilize accelerators in a Spark cluster, Spark needs to be aware of the accelerators assigned to the driver and the executor and schedule them according to user request. Actually, some cluster managers, for example, Mesos, Yarn, and Kubernetes, have already supported accelerators. However, even accelerators are allocated by cluster manager for Spark application. Spark itself is not aware of the accelerators, which cause a series of problems. Consider a simple case where one task needs one GPU. On executor 0, there are 2 active tasks and 2 available GPU resources. Sound perfect. But a resource contention might still happen when these 2 tasks both randomly choose the same GPU card. On executor 1, there are only 2 available GPU resources, but since Spark is not aware of the accelerators, it might schedule 3 active tasks on the executor, and that leads to resource contention, and at least one task would fail. There have been some workarounds trying to make things work on Spark. For example, we tried to only allow one Spark task on each node. Thus, the running task can safely climb all accelerators on that node. But it might lead to resource waste if the workload doesn't need all accelerators. Also, users need to write multi-threading code to maximum data I/O. There are also ideas to let running tasks themselves to collaborate to decide which accelerator to use. For example, they can share with shared logs, but it takes non-trivial effort to implement the solution. Ideally, the cluster manager shall be able to automatically discover resources like accelerators. When the user submits an application with the resource request, Spark shall pass the resource request to cluster manager, and they collaborate to allocate and launch executors. After the user submits a Spark job, Spark shall schedule tasks on available executors, and the cluster manager shall track the resource usage and perform dynamic resource allocation. When the task is running, the user shall be able to retrieve assigned resources and use them in user code. In the meanwhile, cluster manager shall monitor and recover failed executors. To discover and request accelerators, as an admin, I can specify a script to auto-discover accelerators. The discovery script can be specified separately on the driver and the executors. We also provided an example to auto-discover NVIDIA GPU resource. As a user, I can request accelerators at application level. I can use the config spark.executor.resource, a resource name, the amount, and spark.driver, the resource name, the amount, to specify accelerator amount on the driver and the executors. Also, I can use the config spark.task.resource, the resource name, the amount, to specify the accelerator required on each task. As a user, I can retrieve assigned accelerators from task contact. The contact.resources returns a map from resource name to resource info. And thus, it's easy to retrieve all the assigned accelerator addresses. The accelerator-aware scheduling support has been added to standalone Yarn and Kubernetes cluster manager. But for Mesos backend, the feature is still not available. If anyone have interest, please volunteer work on that. We also improved Spark Web UI to show all the discovered resource on the executor page. In this page, we can see that there are GPU 0 available on executor 1. Please note, we keep the interface general to support other type of accelerators other than GPU in the future. For example, FPGA. So GPU is not a hard-coded resource type, and the user can customize the resource type and the discovery script by the config spark.executor.resource name or discovery script. Then context.resources shall return a map from the specified resource name to the corresponding resource information, which contains the resource name and addresses allocated to each task. There are also other features that we considered that should be useful but not included in Project Hydrogen. For example, we shall allow resource requests at task level. Thus, different tasks running on the same cluster can require different resource type or different resource amounts, which would improve the usage of the cluster resources. Also, we can implement fine-grained scheduling within one GPU to further improve GPU usage. Basically, that allows multiple tasks share the same GPUs with a fine-grained scheduling. We shall also support affinity and anti-affinity to decide whether to distribute tasks on as many nodes as possible or the opposite. Let's continue to the second use case we previously mentioned. It requires load the streaming events and then apply predict model on the input data and finally write them back. The major performance concern in this case is to efficiently exchange data between Spark and the AI platform. None of the integration are possible without exchanging data between Spark and the AI framework, and the performance matters. To better exchange data, Pandas UDF was introduced in Spark 2.3, which use Arrow for data exchange and utilize Pandas for vectorized computations. With Pandas UDF, it becomes quite simple to apply a model to a data stream. Simply use pandas/UDF to annotate a passing function that takes pandas series as argument and return another pandas series as the same size. In Spark 3.0, we further enhanced the Pandas UDF improvement to support a scalar Pandas UDF, also be able to return complex type, like a Struct type. This is useful for machine learning workloads, since users can return predict labels and raw scores together now. Another performance improvement regarding data exchange is enhancing data pipeline. Current Pandas UDF implementations only fetch the next batch after the execution of the current batch. On the JVM side, writing next batch to the socket is blocked if the Python side doesn't fetch the next batch. We can prefetch the next batch on Python side to enable data pipeline. In theory, this can achieve 2 times improvement on I/O, and compute balanced workloads, we have observed over 15 improvements in real workloads. Loading model per batch introduce a constant overhead. We propose a new Pandas UDF interface that take an iterator of batches, so we only need to load the model once, and then we can reuse it on an iterator of batches. So here is all. Many ideas in Project Hydrogen are based on previous community work, like TensorFlow, SpeakDL, Apache Arrow, Pandas UDF, Spark GPU Support, MPI, and others. We would like to thank many Spark committers and contributors who helped the project proposal, design, and the implementations. Especially, I want to kudos the following people who made remarkable contribution to the project, like Alex, Andy, Brian, Felix, Hyukjin, Imran, Jason, Jerry, Lee, Maduk, Mark, Robert, Xin, Sean, Takuya, Thomas, Wei Chen, Xiangrui, Xiao, Yi, Yinan, Yu. Thank you.
Jingbo. We got 2 mics on either side. If you have any questions about the project, please feel free. Go ahead.
Hey, thanks, very interesting. Could you differentiate the barrier thingy you did to open MPI in general? Because if I understand correctly, MPI does the communication that you described in the very beginning, so does the barrier thingy.
Okay, let's flash back to the barrier execution slide. Yeah, so previously in Spark, it implemented a map-reduce style execution model, in which model all the tasks in the same stage are actually runs in parallel, which means each task runs separately. They don't communicate with each other. But for machine learning workload, that's not the case. In machine learning workload, it is very common that one task can rely on other task to return some internal data. It computed and then return, and then it continue to fetch data and continue computations. And another difference is that on failure handling, so Spark would retry the failed task while keep the other successful task results. But for machine learning workload, if one task failed, then the whole job needs to be rerun.
Let me rephrase. Doesn't MPI do exactly this communication of a distributed training? So this NCCL, for example, isn't that implemented by MPI?
NCCL is basically from Horovod, which turns the single node computation training workload into a distributed version. And
so what does barrier add? Because I think you wrote somewhere that you run the MPI job. So MPI is the distributed training. So what does barrier do on top of this MPI, which is the communication of distributed training?
You mean how we use NCCL for communication? Yes, actually that's based on the barrier execution mode. So when a task is initiated, the executor 0 will run MPI run, and it serves as task 0, and the other task should initiate connections with that task 0.
Okay, thanks.
Go ahead.
Okay, so we've been using some of this stuff recently, and we really, really like it. We're excited about the idea of using GPUs with Horovod. However, Spark 3 is not released yet. Yeah. So one big question I have is there any plan to backport the GPU support to Spark 2.4? Or if not, when are we going to get Spark 3? Because we'd like this ASAP.
That's a good question. Previously, we have implemented HorovodRunner on top of Spark 2.4, and then we contributed to work with the Horovod community to improve Horovod Spark, and part of the work has been finished. But at Spark side, I think no major changes would be planned in the near future.
I'm referring to the GPU support, which is already in master. So my question is it going to be backported to Spark 2.4? Is the GPU support going to be backported? Is there
he's asking, are we going to backport all the support from the work that's been done with 3.0 back into 2.4?
Just the GPU support. That's
just
the
GPU
really
support.
Since this is a new feature, in principle, we don't backport that to other versions.
Okay. How long do I have to wait for Spark 3?
Undetermined.
That I have no idea.
and even if it comes up in Apache Spark 3, it's still going to be experimental, right? So depending on your situation, whether you want to run it in production or whether you want to just play around with it while you're having a drink or something, that's different.
Okay, thank you.
All right. Anybody else? All right, thanks a lot. Give a big hand to Bingo.